In today's video, we're going to be taking a look at the learning rate finder method. And so this is a really good method for choosing the initial learning rate for training your neural network models, and it's for stochastic gradient descent optimization methods. So let's start with a recap of what the learning rate is. A lot of you will be already familiar with the learning rate. The formula for stochastic gradient descent would look something like this, where theta denotes the parameters of your model. For neural networks, this is the weights in your kernel, the weights and biases of your fully connected layers. And we're iteratively updating these parameters as we train the model. So the new values of the parameters will be the old ones minus some adjustment. And the adjustment is based on the gradient of the loss with respect to the parameters. And so the gradient there is the J prime in the formula. And we want to take a step in the opposite direction of the gradient because we want to minimize the loss. The alpha here is the learning rate. And so we can scale up and down the step that we're going to take in the opposite direction to the gradient based on the learning rate. So if we have a very small learning rate, then we're going to scale down the step that we're going to take. If we have a high learning rate, we're going to have a bigger step because we're timesing up by a bigger number. And so that's going to affect how we change the parameters. So the first question we're probably going to have is, how do we actually set the learning rate? So the learning rate will have different effects on the model and how we're going to iteratively update it. So we start with randomly initializing our weights. And in the graphs above, this is denoted by the point in yellow. So let's first start with the case where we have set the learning rate too low. The graphs that we've got here, we've got the parameter on the horizontal axis. We're just going to start really simple. The parameter here to begin with is just a single parameter. For real neural networks, we can have lots more parameters, but we'll start with a simple case. And on the vertical axis, we've got the loss with respect to that parameter combination. So ultimately, we were trying to minimize the loss to get a better model. So we want to find the minimum point of this loss surface or loss curve. And starting from the yellow point, clearly we can see that we need to reduce this value of theta down until we get to the minimum point of the loss. So if we've got a low learning rate, we first will work out the gradient at the point with respect to the weight, the gradient of the loss with respect to the weight. We see there's a positive gradient, the line is going up, so we take a step down in terms of theta. And we've got a small learning rate, so the step is small. So we're going in the right direction, the loss is reducing, but it takes us lots of steps to get down to this minimum point. On the other hand, if we look at the learning rate set too high, we move down because again the gradient was positive, but we're moving too far. We skip over the optimum point, we reach the other side of the loss curve. Now the gradient is negative, so we take a positive step and we jump back to the other side. Again, we're overshot the minimum point. We've set our learning rate too high. And this, in this case, has led to a divergence in the loss. What we mean by that is that the loss value is increasing rather than decreasing. We want it to decrease to get a better model. Somewhere in between these two extremes, we're going to reach the optimal learning rate, or when it's set just right. So we can take bigger steps, but we still reduce the loss. And here we've reached the minimum point in less steps than if we'd set the learning rate too low. Now that example was very simplified. We had one parameter and it had a nice convex shape. In the real world, when we're training neural networks, this is for a VGG56 model, looks much more complicated. We've got many more parameters. So in this case, we're just looking at two parameters and it's a loss surface because we've got the two parameters and the height we're seeing here is the loss. Many more different structures in the loss surface. It's non-convex. So we're going to have to be much more careful when setting our learning rate here. So how do we determine whether we've set the learning rate too low or too high? In the previous examples where we looked at the parameter space and how the loss surface changes depending on which parameter combinations we have. We're not going to have all those values and all that information when we're training our own model. That was just sort of conceptually what is happening on the loss surface. We're only going to be evaluating at specific points. Actually, if we just move back to this diagram, we're only going to have the loss evaluated at the steps we're taking. We don't understand, or we don't see the whole of the loss curve to begin with. So what can we do? How do we work out whether we've set the loss too high or too low? So when training neural networks, typically we're doing it an iteration at a time or an epoch at a time, and we record the loss at each epoch or iteration. And by plotting this is sometimes called the learning curve, we can determine whether we've set the learning rate too high or too low. There's certain signs in our learning curve that we want to look out for. So the first obvious thing to be looking out for is whether we've set the learning rate too high. So this is denoted by the line in yellow, and we see we start with a loss, and as we progress through the epochs, we actually have an increase in the loss. So this is where the solutions are hopping across the optimum. Our parameter space, we're moving, and the loss is increasing. So this is clearly not what we want, and this is because we've set the learning rate too high. On the other end of the spectrum, with the line in blue, we do see a decrease in the loss, which is good, but the decrease is quite shallow. We're not falling very far. After many epochs, we would reach a small loss, but it's going to take us a very long time to get there, so we can still do a little bit better than this. And then in between those two extremes, we have the green and the red line. The green line would be where we set the learning rate quite high, so we do see a fall in loss, which is good. We haven't diverged. We do see a quick decrease in the loss, which is also good. But then we've limited ourselves to how low we can reduce the loss. We see the loss leveling off. And this is now because we're hopping over the optimum again. We're not diverging, we're not increasing the loss, but it's limiting how low it can go. And then slightly lower than that, we'd get a good learning rate in this diagram, where the loss doesn't decrease as quick as when we had the learning rate slightly higher, but we can reach much lower loss values. So that's preferable. But all of that requires trial and error. So we need to have trained many models to determine what the learning curves are like and whether to increase or decrease. So we can actually do a little bit better than this and automate the procedure somewhat and have a quicker feedback loop. So this is where we introduced the learning rate finder method. And this was presented by Leslie Smith in 2015 in a paper called Cyclical Learning Rates for Training Neural Networks. And the core idea of that paper was to look at certain types of learning rate schedules. We'll look at those in future videos, but they also introduced a very interesting method for determining initial learning rates. It's quite simple, and so what we need is an initialized network, we need some kind of loss, and we need a training data set to optimize this loss against. And we want to take the following steps. So firstly, we're going to be training one batch at a time. We'll take a single batch of data, we're going to do a forward and a backward pass, evaluate the loss. And this is sometimes called an iteration. Secondly, we want to start with a very small learning rate and slowly increase it every single iteration. So the learning rate is always on the move. We don't fix the learning rate to a certain value. And the third point is the fact that we want to be recording the training loss at every iteration. So we want to record the learning rate at every iteration and then the loss that gave you while doing the forward and the backward pass. And then we continue this process until we see the training loss diverge, until we see the training loss increase dramatically. So once we've gone through this process for a given network and a given data set, we want to analyze the results, and from that we can determine the best learning rate to use. So a good way to analyze our results is by plotting a graph. So here we've got a graph of those results for a ResNet 18 model trained on CFAR10. Along the horizontal axis, the bottom axis, we've got the learning rate. And so this is equivalent to the steps that we've been taking, so the iterations. But remember, on each iteration, we increase the learning rate slightly. And so now we can plot learning rate along the bottom axis instead of iterations or epochs. And then on the right-hand side, on the left-hand side, on the vertical axis, we have the loss of the network against the training data. So the things we want to be looking out for here, firstly, we'd expect to see for very, very low learning rates, so 10 to the minus 6, that the loss doesn't decrease much. So we're seeing a plateau to begin with. And this is because the steps we're taking are very, very small and quite negligible. We don't change the parameters enough for the loss to decrease. But then after a while, our learning rate starts to increase as we're going through all the iterations. And when we reach 10 to the minus 3, the changes to the parameters are now significant enough for us to observe a decrease in the loss. And that's why we start to see the decrease in the loss around these learning rates. We keep on increasing the learning rate as we're going through iterations, and we get to 10 to the minus 2. It's still going down. It starts to level off now. So we're reaching a point where increases in the learning rate don't necessarily lead to a reduction in our loss. And beyond a certain point, which is around about 10 to the minus 1, we actually see an increase in the loss. And this is where the loss is starting to spike up and diverge. And when we got to 10 to the minus 0, which would be 1, learning rate of 1, we're actually it's spiking up. We definitely wouldn't want to set the learning rate this high because we're leading to divergence. So based on this graph, our interpretation would be to set the learning rate somewhere around 10 to the minus 2. This is giving us the benefits of a quick reduction of the loss, but not at the expense of a divergence in the loss. So this would be the optimal value. And in this case, we're looking to set the learning rate as high as possible, but just before it diverges, so we could be setting this about 0.5 or 0.05, sorry. So the reason why we use iterations instead of epochs is the fact that we can get quick feedback on whether the loss is reducing, rather than having to wait for a whole epoch to pass before evaluating. So we need to have the ability to run a single iteration for a given learning rate and then get feedback in terms of how the loss is doing. So we want to structure our project maybe slightly differently to what we've got already. So you might have a training script that is defined for a given number of epochs. So we may have 10 epochs that we loop through and train our model. And if we are making adjustments to the learning rate, we might do that only once per epoch rather than per batch. What we need here is the ability to do it per iteration. So they may need some changes to our project structure to be able to do this. So one way to structure your project is with a class. In this case, I've called it a learner. And it needs to have a method that runs a single iteration. So we don't want to define the network and initialize every time we want to iterate, because the iteration should just update the weights rather than do anything else. So all the initialization of our network should be defined in the initialization of the class here. So we've defined the net initialize, defined our loss function, and set our trainer in the init function, init method. And then the main logic we're going to be putting in an iteration method. So again, this whole class is just a construct that can help us structure our project. It's something that I've used to be able to run a single iteration. And we're later going to pass this learner object to the learning rate finder that we've defined, just so we can take a single iteration and get the loss from it. So what does an iteration take in this case? So we want to pass a learning rate given by the LR parameter, and we want to set the learning rate of the trainer to the learning rate that we're passing through. It's the very first thing we do. We want to get the next batch. So we'll see later how we're providing the data loader, because it's slightly different to what we usually work with. And then we just do your typical forward and backward pass. We move to the GPU potentially, we do the forward pass, and we take the backward step, and we have our loss. And here we're just returning the loss, because to do our analysis, we need to be able to see what the loss is for every iteration and every learning rate. So that's why we return the loss in this function. And lastly, we just clean up if we've got any open data iterators. So let's now take a look at the data loader in a bit more detail. When we're moving from epochs to iterations, we no longer have the concept of a full pass through the whole data set. So I've created here a continuous data loader. So first of all, before we look at that, we would just show you the fact that we're working with CFAR 10 from the Gluon data vision datasets, and we're doing some basic transformations. Now that we have a data set, we need to establish our data loader. And a data loader by default would just do random sampling if we specify sample equals true. But we can be more specific about the way that we want the batches to be created. And here, this is the continuous batch sampler that I've defined, and it will keep on giving you batches, a never-ending flow of batches. So you can see we've got a while true loop, and we keep yielding batches when our batch is of the correct size, and we specify the batch size that we want. So now if we were to use this, we first of all create a sampler, which is going to be random samples. Then we want the continuous flow of these samples and batches. So we've defined our continuous batch sampler of batch size 1 to 8, and then we pass this to our data loader through the batch sampler method. So this is just going to give us a continuous flow of batches of size 128, where inside the batches we have random samples. And this is really good for the ability to keep on doing iterations, as many as we want. And later we'll see what defines when we stop our training process. Now the interesting bit. Let's take a look at what the learning rate finder will look like. So the learning rate finder, in this case, the way I've defined it is to take the learner that we've defined previously. So the learner is how we're going to take our iterations for given learning rates, and our learning rate finder will use that method to determine the right learning rate to choose and give us those plots that we've seen before. And the most important method from the learning rate finder I've defined as the find method. So the find method is where the magic happens. It starts with a very, very small learning rate of 1e to the minus 6, and will loop through and slowly increase the learning rate by the learning rate multiplier every iteration until we reach some stopping criteria. So the first pass through find, we set the learning rate to the starting value, and then we're going to loop through. So we're going to go while true. This is a never-ending loop until we hit some stopping criteria. And we take the iteration of the learner with the given learning rate to find a loss. So now we have, for a given iteration with a given learning rate, what is the loss? And we append this to our results so we can do the plotting later, and we can continue this until some stopping criteria is reached. And if we don't stop, then we'll scale up the learning rate slightly by the learning rate multiplier and continue the process until we reach some stopping criteria. And so we'll define that next. And some of the other parts of the function are just so we don't affect the model by using the learning rate finder. And lastly, a function or a method of the learning rate finder will be the ability to plot our results. So now let's look at the stopping criteria. So we said we wanted to increase the learning rate slowly and keep doing more and more and more iterations until we see divergence. So this is where we define what we mean by divergence. In our implementation here, which I found works quite well, is that we will stop when the loss reaches twice the initial value. So we're expecting the loss to fall from an initial starting point, but when we see the loss go higher than double our initial starting point, then we're going to stop the process. But instead of just looking at a single loss value, we're going to take a running mean. And so some of this logic and the smoothing factor is just to get a running mean of the loss. And so when the running mean is greater than the first loss times 2, that's when we're going to stop. Another condition is the fact we want to take at least a minimum number of steps. We want to do at least 20 steps and then we can stop. So now that we've defined the stopping criteria, we know when to stop. So with everything defined, how would we use these? And it's actually quite simple now. So the first thing we do, as we do with all MXNet models, is we define our context. This chooses where we want to run the model. If we've got GPU available, we'll be using that. We define the network that we want to train. So we're just taking a model straight out of the Gluon Model Zoo, and it's a ResNet 18 v2. Because we're working with CFAR 10, we're going to have 10 classes. Then we've previously defined the data loader, so we pass the data loader and the network and the context to our learner. And so when we initialize the learner, we're going to initialize the weights of the network, we're going to set up our trainer and ready for the iterations. So we pass our learner to our learning rate finder and we can start the find process. So here we're defining that we want to start the first iteration with a learning rate of 1e to the minus 6 and then work up from there. Great, and so now we have a plot of the learning rate versus the loss. And as we saw before, we have a plateau at the beginning where the learning rate is so small that the updates to the parameters are negligible. And then we reach a certain point where we see a significant decline in the loss up until a point where we see divergence. So based on this chart, for this particular model, ResNet 18, for the CFAR 10 training, we would like to set our learning rate to approximately 0.05, which is the highest learning rate possible before we see the divergence. So based on this, let's use what we found as the optimal learning rate and set this for training our model. So we want to set the learning rate to 0.05 and we're going to take 500 iterations. Again, we're using our learner here and we're going to log the loss every 100 iterations. So let's run that now. So our loss starts at 2.7 and then we see that the loss falls, which is a good thing, and falls relatively quickly. And we reach a final loss after 500 iterations of 1.06. Let's experiment a little bit. Maybe we want to see what would have happened if we had set the learning rate slightly differently. So here, if we set the learning rate too high, to 0.5, maybe we see divergence or a loss not quite as low as before. So let's run that now. We're loading the parameters, so we're starting from the same point as in the previous example to avoid the initialization being an influencing factor. We do see a decrease in the loss, which is good. So this is before divergence in terms of how we've set the learning rate. But we haven't reached quite a low final loss as we had before. The previous example was 1.06 and here we've got 1.18. So it's not a huge difference, but maybe we'd see if we trained for many more iterations that the loss here would have leveled off and wouldn't be decreasing, while at 0.05 we might have seen a decrease. And now let's have a look at the opposite end of the spectrum if we'd set the learning rate too low. Instead of 0.05, we add an extra 0 and we go 0.005. Again, starting from the same initialization parameters. So we have the similar starting loss after the first iteration, and we see the decrease, but the final loss doesn't get quite as low after 500 iterations. We would expect the loss to reach a much lower value, but because we've set the learning rate very low, it's going to take a lot longer to get there. So a good balance was 0.05, which we found quite quickly by using the learning rate finder method, and much quicker than we would have done by trial and error and training our model to convergence each time. It gives you a very good idea of where to start, so you're not shooting in the dark from the beginning. And so yeah, thanks very much for watching the video, and look out for future videos on how to set learning rate schedules, because this is an important factor when determining how to set your learning rate too. Thank you.